And now I will show you how we can estimate the model using the sample data at hand. So to do that, we will use the least squares estimator, and the model, the regression model that we will be estimating will look in the following way. So y, the dependent variable, is a function of beta 0, which is the estimated value of the intercept. And we know that beta 0 with the hat is a sample parameter because it has a hat, and we already know from the past that whenever we have a sample value, it has a hat, and whenever we work with population value, it doesn't have a hat. Plus beta 1, the slope, so the estimate of beta 1 multiplied by the value of x, which is the independent variable plus the epsilon, which is the error term. We can rearrange this equation to get an expression for the epsilon, for the error term, and it will be just y minus beta 0 plus beta 1 xi. So in other words, what we do is we take the actual value of y and we subtract its predicted or estimated values based on the estimated model. So the error term is equal to the difference between the actual value of y and the one that we the one that we have in the data set, minus the predicted or the estimated value of y. And after this, we can obtain the so-called sum of squared errors. To do that, we just sum the squared difference between the actual value of y and its predicted value. And this least squares estimator works in such a way as to choose beta 0 and beta 1 so that the sum of squared errors is as small as possible. The reason is very simple. The error that we've got here shows the difference between the actual value of y and the one that we have predicted using the model, and we would like the prediction to be as close as possible to the actual value, so we want the error to be as small as possible. Therefore, this estimator chooses beta 0 and beta 1 so that the errors are as small as possible. And here are the formula that we will use to estimate beta 1 and beta 0. Beta 1 is just the ratio of these two values, and to estimate them we will use these two formulas. So for the value from the nominator, we will use the following formula. We will sum the product of two differences. The first difference is the difference between x, so each value of x and its sample mean, and the second difference is the difference between each value of y and its sample mean. Here is another possibility for estimating the value from the nominator. To do that, we can sum the product of x and y, so x multiplied by y for each observation, 1, 2, 3, 4, 4. After this, we sum those values and subtract the product of the sum of x values and the sum of y values divided by n, which is the sample size, so the number of observations we have in the data set. And to get the value from the denominator, we will sum the square difference between individual value of x and the sample mean. Or the alternative formula looks like this: the sum of squared x's minus squared sum of x's divided by the sample size n. And to interpret the estimates of beta 0 and beta 1, you can use this guideline. So beta 0, which is the y-intercept, represents the predicted value of y when x is equal to 0. So we say that y, the dependent variable, is equal to beta 0 when the value of x, the value of the independent variable, is 0. And beta 1, which we know is the slope, it represents the increase or decrease in y given 1 unit increase in x. So in other words, when x increases by 1 unit, y, the dependent variable, will either increase if beta 1 is positive or decrease if beta 1 is negative by the value of beta 1.